Hi AP Stats, this is Mrs. Harding. This video is going to cover lesson 11.2a on the chi-squared test for homogeneity. If you want to really quickly look at the learning targets, it's these here at the top. State an appropriate hypothesis and compute the expected counts and chi-square test statistic for a chi-square test based on data in a two-way table. We're going to be looking at two-way tables in this video. State and check the conditions for data in a two-way table, calculate the degrees of freedom for a test based on a two-way table, and then in general, learn how to perform a chi-square test for homogeneity. So let's get started. You can find 11.2a in your OneNote notebook. And if you look at the top, the question there that we're going to think about says, suppose that the Chicago Public Schools randomly surveyed some of its graduating seniors to determine plans for graduates after high school. We might wonder if the plans of students have stayed the same over time. Suppose the two-way table given below represents survey results. So you can see the information that we have here in the two-way table. There's two different variables. There's the plans for after high school, and then there's the year that they collected the data. 1990, 2000, 2010. And you have all of the totals in there. What we're going to do with this is, because the sample sizes are so different in each of the years, we're actually going to take a look at the conditional proportions rather than the counts. So what you see in this next table is the percentages of each year that had certain plans after high school. So for example, college in 1990, in our counts we saw that that was 320 people out of 453 that were surveyed that year. So 320 out of 453 is about 70%. So we're going to take a look at this because the totals in all of the categories are so different that comparing the counts wouldn't really give us useful information. So instead we're going to take a look at this where it gives the percentages. And then you can see in here that the percentages are different. So in 1990, about 70% went to college. In 2000, about 84% did. In 2010, 91% did. So there is some evidence there that these proportions are changing. But the question really is there a statistically significant difference in the percentage of post-high school choices across these decades, or are these differences due to what we would expect just by chance alone? There's going to be variation from year to year, so is this just that expected variation, or are these differences actually significant? Okay, go ahead and scroll to the second page. Some of this might seem like we've done it before. We've certainly compared proportions. In the previous chapters, we did two sample z-tests for proportions, but the difference here is that we have multiple proportions from multiple populations. So when we're faced with comparing all these multiple proportions, what we're going to perform now is called a chi-squared test of homogeneity. You guys know what that word means? It means the same. So we're actually looking to see if these proportions are the same. So we're going to look at this and see if the proportions are the same for these three graduating classes. We're going to talk about a null hypothesis, and the null hypothesis is that they are all the same. And then there's an alternate hypothesis that would say they were different. Now these differences could be one major difference in one area, or it could be a bunch of small differences in several areas. And down below you can see a segmented bar graph. Just kind of confirming what I said on the previous page, there is some evidence here that there has been a change over the last 20 years in students' plans beyond graduation. You can see there that the proportion of students going to college seems to be increasing over time. Okay, so let's start talking about the actual parts of the test. I mentioned the null and alternate just a second ago, but the null hypothesis for this test that we're about to perform is that there is no difference in the distribution of proportions of CPS students post-high school plans for the 3 years. And then alternatively, our alternate hypothesis, there is a difference in the distribution of proportions. You don't have to get any more specific than that, just that either there is no difference or there is a difference. So one of the things that we're going to need to figure out to perform this chi-squared test is what the expected counts are. It says the chi-square statistic is calculated the same way as it was for the goodness of fit test. We're doing a sum of observed minus expected value squared over the expected value to get the chi-squared test statistic. We have all the observed counts from the original table. So what we need to do is then just figure out what the expected counts are. So how do you do that? So if we look at just the military for 1990, it says consider the expected counts for military 1990. There are a total of 42 in the military category across all 3 years. Let me just scroll back up there for you so you can see what I'm talking about. So we're looking at the military category. Overall, there were 42 students in those 3 populations that went into the military. So 42 out of our table total of 1,058 is what we would expect. Oops, almost went a little too far there. So 42 out of 1058 is about 3.97%. We would expect a little less than 4% of the students to have gone into the military. We're going to use that percentage to determine our expected counts. So we would expect that 3.97% of those students in 1990 to join the military post-high school. There were 453 students surveyed in 1990. We would expect then 17.983 of these students to join the military in 1990. So we just took the overall count of how many students went to the military out of the total and then applied that proportion specifically to 1990 to get that we would have expected a little less than 18 students to have joined the military. But now think about these calculations again, because there's a quicker way to get to this, like there always is, right? If you look at the math that we just did, 42 over 1058 times 453, where are these numbers in the table? These numbers, 42 is the row total for military, 453 is the column total for 1990, and 1058 is the total of the entire table. So coming up with an expected count for any individual cell in the two-way table can be found by doing row total times column total over the table total. So you can see in this next table, so we're going to scroll down, some of them have been calculated for you. Well, and if you're looking at the answers that I'm showing you, they've all been calculated for you. But that is how these numbers all came about. So you can see right here the 17.98. But for ones that are missing in the blank copy, look at employment in 2000. Well, employment in 2000, I would find this expected value of 38.10 by doing row total 139 times column total 290 divided by 1058, and we would get about 38.1 people would be expected to get a job directly after high school in the year 2000. So once we have all of those expected counts, one of the conditions for this test for homogeneity is that all of the expected counts are at least 5. So looking through the table, we can verify that yes, all of these expected counts are at least 5. So then if we move forward with calculating the test statistic, you can see the pattern there for each cell in the two-way table. It's the observed value minus the expected value squared over the expected value. The sum of all those things leads you to 72.77. This is the chi-square statistic. But just like for the chi-square test for goodness of fit, we need to know the degrees of freedom. And there's a pretty simple way to figure that out. The degrees of freedom is the product of one row minus 1 times column minus 1. So in this case, that's 2 times 3. So this would be 6 degrees of freedom. Okay, then moving on with the test, scroll to the next page. And for any test that we're doing, we need a p-value to draw a conclusion about our samples. So to determine the p-value, you're going to go to your calculator and you're going to go to the distribution and you're going to select the chi-squared CDF. This first value is your test statistic. Second value is a large number. Remember, in the chi-square distribution, we're always looking from our test statistic to the right. So it's always this area between those numbers, and 6 degrees of freedom. And you should see that you come up with a very, very, very small number. You can pause the video and just verify that you can find those commands in your calculator and that you get that value. Now that's a pretty small p-value. So we're going to reject the null hypothesis and conclude that there is evidence of a difference in the distribution of proportions of CPS students' post-high school plans for the 3 years. Now let's just take a look at a summary of what we all did. We started with writing our hypotheses. First, the null hypothesis is that there is no difference in the distribution of a categorical variable for several populations, and the alternate is that there is a difference in the distribution of the variable for several populations. The next thing that we did is we went through and we found the expected counts for each cell. And remember how we found the expected counts. We did row total times column total divided by table total to get the expected count for any one cell. And then summing up all of these calculations will give you the test statistic. And then we went to find the p-value using that test statistic. The p-value is always from our test statistic to the right. And we found the degrees of freedom by doing number of rows minus 1 times number of columns minus 1. And this gives you the p-value for the test. Now, with any inference test that you do, there are a set of conditions that have to be met. And those conditions are here. We need to have counts, which we had. The random condition does need to be met, so these need to come from separate random samples or from random assignment in an experiment. The large sample size, this is where all the expected counts that you find need to be at least 5. And then, of course, there's the independence. The samples or groups themselves and the individual observations in each sample are independent. Remember, when you're sampling without replacement, check that the individual populations are at least 10 times as large as the corresponding samples. When you're not sampling without replacement, like when you use volunteers for an experiment, you just check that it's reasonable. The independence condition is based on the method of assignment, which is hopefully random assignment. We can also do this test in your calculator using matrices. So go ahead and get your calculator out if you haven't already so that you can take a look at this method and you can find these commands. Okay, so the directions for how to do this are there at the bottom. You can do this by going to your matrix menu. Remember where you find that on the left side, second x to the negative 1, I believe. And you're going to edit matrix A. And here's where you're going to put the observed counts. So you can see on the screen what all these observed counts are. If you want to stop the video and try this out on your calculator, get this entered in. Once you have those observed counts, the next place that you're going to go is to Stat Test, and you're going to scroll down to C and select the chi-squared test. In this screen right here, it will default to A and B, but the great thing about this is you don't have to figure out the expected counts. You're just telling the calculator to figure them out and to put them in matrix B. So for some reason, when we get to the end of this test, you need to see what those expected counts are, such as when you're verifying conditions. You can just have your calculator tell you what's in matrix B, and you'll be able to see what the expected counts are, but you don't have to figure them out for yourself. And so then when you go to the bottom, you can either calculate or you can draw. The draw then would be showing you where it is on the chi-square distribution. So you'll get this here. And you can double check our test statistic, 72.77, our p-value, remember that very small number, degrees of freedom is 6. Now you can't see it in this picture because our p-value is so very small, but if it wasn't such a small p-value, you would actually see a spot on here with shading to the right to show where exactly the sample falls on the chi-square distribution. And if you need to verify what the expected counts are so that you can check off that condition there, you can always go here, go second, go to the matrix. See how it has it filled in as a 4x3 right there? I can just put B on the screen, hit enter, and it will tell me what all of these are. And I can scroll over to make sure that everything in there is at least 5. So you can do that to check for the conditions. Now, at the bottom of this page, there's a practice problem to check your understanding. Go ahead and pause the video. I want you to try that out. you can use your calculator commands. A comment about using the test and the calculator, though, is that you will need to write out a few terms of the chi-square test statistic. So if you remember back up here, you can see that a few of these terms were written out, the first two and then the last one. You don't have to calculate this by hand. You don't need to write all of the terms out because you're just going to go probably to the test to get that test statistic anyway. But you should get in the habit of writing a few terms of that formula out. So again, go ahead and hit pause. Give this last one a try without looking at the answers, and then when you think you have it, you can pull up the answers. Ooh, I'll show them to you. Pull up the answers in your OneNote. Just a brief overview of the answers. You have your null and alternate hypothesis. The null is that there's no difference in the proportions of the wine types purchased when different music is playing. Alternate, there is a difference in the proportion of wine types purchased with different music. All of the expected counts are at least 5. This is where if you're doing it in your calculator, you're going to have to take a look and see what's in matrix B, or you could calculate these by hand also, but they were all at least 5. So that's hypotheses, conditions, the treatments were randomly assigned, so randomness is met. Because the treatments were randomly assigned, independence between subjects is reasonable. We're not going to check the 10% condition. This was not sampling without replacement. Then the calculations, you have your chi-squared statistic. Again, the first two terms, the last term. You get 18.3, degrees of freedom is 4. Doing the test or doing a chi-square CDF gives you a p-value of 0.001. So assuming a level of significance of alpha equals 0.01, we have convincing evidence that there is a difference in the proportion of types of wines depending on what type of music is playing. As always, if you have questions, please let Mr. Bowman or I know in class. Have a great day.